is written, and he will together and improve 3D adaptive learning system for brain tumor segmentation using multi-model MRI as a
Good afternoon, everyone. The paper I present today is an improved 3D UNet-based deep learning system for brain tumor segmentation using multimodal MRI and from the journal Multimedia Tools and Applications. The purpose of the study is in proposing an improved 3D UNet system which can effectively segment brain tumors and their subregions from MRI automatically. And they divided the subregions into three parts: the whole tumor, tumor core, and the enhancing tumor. In summary, the proposed 3D UNet can effectively integrate four types of MRI modalities. It's T1 contrast, T2, and flare. And it provides accurate segmentation of tumor regions and shows strong generalizability. However, the segmentation of the enhancing tumor remains the most difficult due to its features. Next introduction. The study used the breast data set. It comes from the multi-model brain tumor segmentation challenge 2018, which includes multi-model MRI scans, the T1 contrast, T2, and flare. Labs were collected from 19 different institutions. And instrumentation ground truths. The green part represents edema, and the red is the tumor core, and yellow is the enhancing tumor. And these are the reference labels for training and evaluation. The study uses two data sets. First is the breast 2018 ECO dataset 1 with 210 HGG and 75 LGG, a high-graded glioma and lower-graded glioma. And the dataset 2 is a local dataset with 71 subjects. And values of all of the MRI are 240 by 240 by 155. And it all includes four modalities. And the pre-processing of the MRI, including cropping the image to 128 by 128 by 128. And second pre-processing is Z-score normalization. And third is data augmentation, including flipping and rotation. And the study replaced the standard 2D UNet architecture with a fully 3D version. It means they use a three-dimensional kernel. And the modified network contains multiple convolutional blocks designed to process 3D values more effectively and capture volumetric important features in the tumor localization. And this slide shows the architecture of the proposed 3D UNet. It includes the encoder path and the decoder path, and its symmetrical layers. In the downsampling, this low arrow, the downsampling is done with using max pooling, and upsampling is done through transpose convolution. And the skip connection, you can transfer the volumetric detail from the encoder to the decoder. And each convolutional net block contains 3 by 3 by 3 convolutions kernel, and followed by a green cube represents the transition layer. And the convolutional net block, in every layer, it can create a feature map, and the number of the feature map means it can catch how many features in these layers. For example, it catches 16 features in the first layer, and down by layer, it finally can catch about 1,000 features for recreating the output results. And this transition layer, it is a key innovation of the study. They place this layer by each convolutional block. It means the input and output is the convolutional block mentioned here. And the transition layer includes a batch normalization and ReLU amplification function. And next is a one-by-one convolutional layer. It can reduce the channel reduction and reduce the parameters of model and the amount of calculation. And the third is a 2x2 average pool. It can also do the downsampling to reduce the size of feature map, and it can smoothly keep the information. And this study divided brain tumors into 3 parts: the whole tumor, the tumor core, and the enhancing tumor. And the whole tumor means the whole tumor area, and the tumor core means the tumor in the whole tumor, but excluding the edema region. And the enhancing tumor means the highlighted areas of T1 contrast match. And the highlighted area usually means that there is some inflammation or lesions. And the performance metrics, they use 4 metrics to evaluate performance: the DSC, sensitivity, specificity, and AUC. And the DSC means the overlap between the prediction and the ground truth. The sensitivity means it's the model's ability to detect the actual tumors. And the specificity means the model's ability to avoid false positives. And the AUC, it means the estimate overall classification and ability of the model. And all of the metrics, the range is 0 to 1. And this is the results. It compares the dataset 1 and 2 and dataset 2's results first. And the segmentation on dataset 1 is better than dataset 2. And one major reason is that the dataset 2 include the lower dataset 2 include a 1.5 T MRI scans with lower signal to noise ratio, and it leading to the blurry features and poor resolution. And this makes it harder for the model to detect tumor boundaries. And the model's training and validation loss and accuracy is these 2 figures. And we can note that the training and validation loss decreased sharply within the first 5 epochs. And it is stabilized after the 10th epoch. And this indicates that the good convergence and training stability. And this figure shows the segmentation samples from dataset 1. And the predict mass closely match the ground truth, especially with the WT and TC regions. And this confirms the model's reliability on high-quality data. And for dataset 2, the model showed lower accuracy and higher loss for dataset 2. The main reason of this low results is because dataset 2 is insufficient data. And the study says that and after applying data augmentation on dataset 2, and the performance didn't improve for the deep learning systems. And the second result is it compares their proposed 3D UNet to the standard CNN and the standard UNet. And the result is adding the translation layers and the batch normalization, it can significantly improve the dice stores across tumor regions. And in the this figure A and B is the AUC curve. And if the curve is closer to the upper left corner, it means that its performance is better. And the area under the curve in the dataset 1 in these three architectures is not much difference, but the true positive rate of the proposed 3D UNet is slightly higher. And in the dataset 2, it have the same results. It also have a higher true positive rate, and it is closer to the upper left corner. So its performance is better than the other standard CNN and standard UNet. And they compared the model with the top 3 models from the BRAS 2018. And the first is Mironenko. It applying the big patches of the MRI images. And the second one is Sensi. They use the standard three-dimensional UNet. And the third one, they also segmenting the tumor into 3 subregions, and they modify the matrix by this method. But they use small patches of MRI image. And this proposed 3D UNet, its performance is better than these three models in the whole tumor area and tumor core area segmentation. And it means that this proposed model can achieve the competitive results and using a simpler architecture. But the result of the ET is slightly lower than the third methods. And I think the possible reason is this method of the post-processing is not suitable for enhancing tumor region, but the performance was still comparable. In this discussion, it says that the dataset 2's weak results are due to the limited data and the poor signal-to-noise ratio. And the ET region remains the hardest to segment. So the study suggests that it can improve the ET region's segmentation's performance. And through the first one method, we can train the model by using the ROIs as input instead of the whole image. Or the second method is use another post-processing techniques to improve segmentation performance. Thanks for listening.
Any questions?
I want to ask you page 17. I was wondering, they compare different machine learning models, and did they do a comparison between the p-value to compare? Is there any statistical differences?
It didn't mention that they have a p-value or other statistical results.
Page
12.
I want to ask what is the loss function in the two features?
The loss function is like 就是类似说我们定出一个例如说计算误差的方法，那我们在训练过程中就是会尽量让那个会在它训练的过程中让它的 loss function 越来越小，就是类似于让它的误差越来越缩小的意思。
然后问题7页的就是还有问题就是它左右两边那个 encoder 跟 decoder，它们两个是什么意思？然后差在哪里？
在 encoder 的部分是类似于说它去用一个 kernel， 就是那个 convolution， 然后它去扫整张影像，那就是它会在扫的过程中，那它会就是因为比如说整张影像是刚说的128×128，然后比如说我用3×3的 kernel， 然后在每一个3×3的部分，它会提取它里面认为它重要的特征，比如说这个3×3部分，其中一块它比较亮，或是它的形状跟其他不一样，那就是它会提取出这个特征来，然后就会保留在这个 feature map， 然后它就会依照这个顺序，然后把这个 feature map 做得越来越大，就代表它保留的特征越来越多，所以它就把它命名成 encoder。然后 decoder 部分是它用刚刚这些提取到的特征，再加上这边的 skip connection， 它比较像是它保留它的 whole image， 它保留它的整张，就是它把从这里输入的影像直接传过来这边，那就可以同时有原本的影像加上它提取到的特征，然后它用这两个资讯去还原出它要切割的部分，然后到这里之后，它这个地方是再用一个分类的方法分类出它是 poor tumor core 或是 enhancing tumor， 然后再把它的分割的结果输出出来，这样。谢谢。
就是最下面的那个灰色的那个方块是对应上面的原则设计位置。
这个灰色方块就是刚提到的那个3×3的那个 convolution 的 kernel， 那就是他用这个方块去提取整张影像的特征出来。
The same page. How does the white rectangle represent like existing for 32 and 60?
And the black rectangle means the feature就是黑色的方块是指它从它的 feature map 里面提出的特征，那白色的部分是它从 skip connection， 就是从原始的影像，然后再是它 它 max pooling 之后产生的新的影像的特征。那它把这两种不同的特征同时做参考，让它从这边的最后跑出来的影像，然后慢慢还原成它原来大小的影像。所以你可以把黑色跟白色都看成是一种保留特征的东西，然后可以同时从这两个地方提取特征出来。
What difference between HGG and LGG?
HGG 是指说它的HGG 和 LGG 都是指恶性的脑瘤，但 HGG 是相对严重的，分级是相对严重，然后 LGG 是相对比较轻缓一点，就是 HGG 的侵害性跟危及性都比较高，那 LGG 是比较低。
This model is suitable for other cases.
It only mentioned in the brain tumor and not other organs.
Same page. You mentioned that now max pooling just takes the important information. Why is it that in the encoder part, the features gets more?
它比较像是你从原始的影像，然后你提取部分的特征之后，再来它会用一个 max pooling，就是 max pooling 就是类似说这是原本的影像，那我用一个 2 by 2的 kernel 去扫过每一个部分。那比如说在这里，因为它叫 max pooling， 所以它会保留这个最大的数字。那你可以把它想成说这个部分里面它最重要的资讯，它就把它保留出来，然后它就这样子一直下去，一直到跑完整个影像，那就会得到一个尺寸是原本的1/4。然后这是一个相对原本来说是一个新的影像，然后再从这个新的影像去提取新的特征，然后就可以越缩越小。那这同时它提到的特征就会越来越多。
我几个问题想问，就是第一个为什么这个研究选择就是传统的 CM 的，而不是后续出现的非得 RC 等等的？它有什么优势？
他可能是想表达说，因为他用的模型是就是你可以把这个绿色方块遮住的话，它就是原本的经典的模型。那他可能是想表达说，他只是做了这个小改动，那他就跟没有改动过的 master 来做比较。它应该是这样的，应该是这个意思，所以它有同时比较那个刚提到的其他3个研究提出的不同的模型。
那第二个问题是，就是它这个研究是使用Vertex 的218跟小型的本地的资料集嘛？
是。
那我们如果今天用的是不同的扫描，比如说1.5T 的 MRI 跟3.3T 的 MRI， 那这个对我们的模型的泛化能力会有什么影响？
它里面提到的意思，它没有详细说明说它的 training set 或是它用的资料是来自磁场强度多少的仪器，那只有提到说它用到了 1.5T 的跟3T 的，它只有说要提到这2种，所以我觉得它的泛化能力可能就仅限于这2种磁场强度的仪器这样子。
那最后一个问题就是，如果我们想要提升，因为他这边讲到总有那个 EP 区的分割效果，那如果我们想要 提升这个效果的话，我们除了扩充资料跟后处理的部分，那你觉得我们引入这个注意力机制是有效果的？
就应该可以，因为它是一次看一整张肿瘤的话，那应该会比 CNN 或是 ULAN 还要再更好一点。但它主要是提说他想要针对他因为他后面的 discussion 都是在对影像本身做优化，他就没有提到，比如说换一个模型。但是如果说换成 self attention 的话，因为他每一次都是看整张图，那应该会比这样子慢慢扫来的更有效果，或是比较好去看出它的边界。
I have a next question. What's the paper related to your research?
因为我的研究也是跟脑瘤有关，然后它的分割方法也几乎跟我要用的分割方式相同的，所以我才找这个资料。
我想要问说，就是他好像没有提到实际肿瘤的大小，那大概如果肿瘤很小的时候，使用这个会不会有什么影响？
我觉得肿瘤很小的话，可能会造成影响，是他提到的例如说影像本身太模糊，或者是它的讯噪比太低，所以就会造成它很难分辨出有肿瘤的区域跟没有肿瘤的区域。所以如果肿瘤太小的话，可能就是会因为主要因为影像模糊，然后造成它可能会影响到这个部分。
Thanks to his presentation.
The next speaker is Xie Yuzhen, and her topic is positional emission tomography.
I'm today's presenter, Xie Yuzhen, and today I will share my research in dose verification in proton therapy using positional emission tomography. And since I have been working on this topic from my undergraduate studies, and my graduate research will continue to build on it, so I have some results to share. And this is my outline. I will start from the introduction and my material and methods, and then it's my results and my future work. So first part is introduction. And proton therapy is one of the most precise forms of external radiation therapy. And proton beams deposit most of their energy near the end of their peaks, forming a bright peak, like here. And compared to proton therapy delivers a much lower entrance dose and minimizes radiation beyond the target volume. Thanks to this unique depth dose characteristic, proton therapy provides highly conformal radiation to the target, However, due to the steep dose gradient near the red peak, range uncertainty can have serious consequences such as damaging healthy tissues or underdosing the tumor. And therefore, the real-time monitoring and verification for proton range are crucial to ensure the safety and accuracy of treatment delivery. And positron emission tomography, which is PET, can be used for proton therapy verification because when a proton beam enters the human body, it activates elements such as carbon, nitrogen, and oxygen along the path and producing positron-emitting isotopes. And PET scanner can image the distribution of these activated isotopes within the patient after proton irradiation. And since proton-induced nuclear reactions are highly correlated with the proton dose and range distribution, PET imaging of activated isotopes can be used to estimate the proton beam range and the dose distribution, enable verification of proton therapy delivery. And currently, there are many methods for verification, but all verification methods, including multi-tower simulations, analytical calculation, and deep learning approaches, have their limitation. So the multi-tower simulations are extremely time-consuming and are mainly used for research purposes, not yet fully implemented in clinical range verification systems. And about the analytical methods, such as Gaussian-Parlow convolutions, are based on simplified model assuming uniform materials and only predict positron distribution near the distal end of the dose, and leading to large errors when applied to real patients with heterogeneous tissues. And the deep learning methods rely on supervised training use specific data sets, making them less stable and only applicable to certain conditions, which limits their general reliability. And MC² is spatially optimized for fast and accurate proton dose calculation, completing a full IMPT plan within 3.5 minutes. It has been adopted in some clinical centers for independent proton dose verification. And based on MC², my research lab developed a physical model for positron emitter production, leading to MC² PE, a fast synchronized proton dose and positron activity calculation system for range verification. And next part is my material and methods. So overall, my methods have two parts. So first part is development of MC² positron distribution calculation model, including the data set of perception for proton-induced positron nuclear activation and the calculation of positron nuclear yield distribution. And next part, I will do the validation with GATE Monte Carlo and the experimental measurement data from Kaohsiung Chang'e Memorial Hospital. And GATE is a Monte Carlo simulation platform built on the Gen4 toolkit, and it is usually validated application extensively applied in medical physics, and including SPECT and PET image simulation, and more recently in CT images and proton dose estimation for patients. The positron activity simulated by the GATE software is used as a benchmark to validate the MC²P software developed in my study. And for the first part, during proton irradiation, the protons not only deposit dose via the electromagnetic interaction, but also undergo inelastic nuclear reaction with tissue elements and will produce the beta plus isotopes. And the main elements in the human body are carbon, hydrogen, oxygen, and nitrogen. And as shown in table 1, the major proton-induced positron-emitting nuclear reaction channels include only 6 channels. And the probability of elastic nuclear interaction between protons and atomic nuclei is described by the nuclear reaction cross-section. And each reaction channel has its specific cross-section. And for my study, I choose to use cross-section data provided by Nuclear Data NDS. NDS database is maintained by the U.S. National Nuclear Data Center and under the supervision of the International Nuclear Data Committee. It's one of the most authoritative nuclear data sources and widely used in the nuclear physics, radiation medicine, nuclear energy, and proton therapy. And the figure Y shows cross-section of carbon-11, oxygen-15, and nitrogen-13, producing under 6 reaction channels as I mentioned before. And the MC² software records the proton fluid at each collision point, which is often represented as particle track length density in Monte Carlo simulation, and use the previously defined nuclear reaction cross-section, sigma x to y, where x is the target element and y is the resulting beta plus isotopes from inelastic collisions. And we can compute the yield is Ny of each isotope is a given Boxel delta V by interpreting over the incident proton energy spectrum, and as shown like this formula. And this figure shows the planned workflow will first develop a positron distribution calculation model within the MC² software. And this function will utilize particle information recorded after collisions, and based on the previous equation, will calculate the positron yield distribution for each nuclear reaction channel. And since I focused on 6 nuclear reaction channels, the 6 positron yield distribution images are expected to be generated during the process. And finally, the distribution will be superimposed based on the products to simulate the positron yield distribution for carbon-11, oxygen-15, and nitrogen-18. And MC² is primarily implemented in C language, and it supports operations through a command line interface, graphical user interface, or integration with Python via the function code. And users only need to enable the score positron emission in the MC² configuration file to activate the positron distribution calculation function and generate the positron yield distribution. And this is about the beam model optimization with clinical data. And commissioning is essential when installing a new proton therapy system. So the beam data library plays a critical role by providing key parameters for beam modeling. And these data are used in treatment planning systems like Monte Carlo engines like MC². And the model optimization focuses on these 3 parts, including the phase space, talk about the spot size and divergence. And the energy spectrum, talk about the mean energy and the spread, and also the absolute dose calibration. And the figure 2 is trying to illustration of beam optics in the XZ plane, and the beam size variation along the beam axis due to the angular divergence. And this is the angular divergence here. And next is my results I have. So the first part is about the dose verification in the homogeneous HDPE phantom. So using the MC² based development software along with the clinical treatment planning software GATE and RayStation, we perform simulation analysis of proton dose depth distribution within the 70 to 210 MeV energy range. So on the left of figure 3, I have the rapid distribution for the 70 to 130 MeV energy level. And on the right, we can see the results for the 140 to 210 MeV range. And this graph clearly shows that the calibrated MC² simulation software is highly consistent with gates and the base station, and demonstrating the stability and the accuracy of the physical modeling and numerical methods. And the right figure, I also present the dose intensity distribution for proton beams at 70, 100, 150, and 200 MeV to examine the dose distribution capability at different energy levels. And next figure 5 compares the proton range, the RAT prediction from MC² gates and radiation as different energies. And all these three software show high consistency, with range differences under 1.2 millimeter for energies below 210 MeV, and around 2 millimeter above 210 MeV. And these small discrepancies are due to differences in energy calibration and calculation methods. And about the figure 6 regarding the bragg peak FWHM, MC² align closely with radiation, with the median differences near 0 millimeter, and the IOR is 1 and 2 millimeter. And in comparison, the MC² and gates shows the median differences of minus 1.2 millimeter, with an IOR of minus 0.2 to minus 2.2 millimeter. And since radiation is optimized based on clinical data, it serves as the reference, and MC² predictions are more accurate in the FWHM. And next, the figure 7 shows the lateral dose distribution for MC² gates and radiation. And at the low energies, MC² and gates differs more, but at the high energies, the distribution align. And the figure 8 shows the FWHM trend with the energy, and except for 70 MeV, where the differences is larger, and the FWHM differences are within 2.5 millimeter for the other energies. And the MC² media FWHM differences with radiation is 0, while with gate is minus 2.3 millimeter. The large discrepancy with gate is likely due to the differences in beam parameters, and because gates use beam emitters in the simulations. And this is about the positron isotope yield distribution verification. So about the figure 9 shows the distribution in the distal range region are highly consistent between the gate and the MC², and however slight differences remain in the proximal region. And we suggest that these differences may arise from the delta tracking various reduction technique used in the MC², and which could affect the yield rate and result in small shifts in the distribution. And look at the figure 10. The simulation results shows that MC² and gates are highly consistent in depth and lateral activity distribution, confirming the accuracy of the method. And when compared with the experimental measurements, the distal range shows good agreement. The average of delta R50 is small than 2 millimeter. However, in the proximal range, especially of high photon energies like 200 MeV, there are noticeable differences between MC² and PET measurements. And these differences are likely because the simulations doesn't yet include the positron range and PET detection system modeling. And thus, I also do the comparison of simulation calculation time between the MC² and get these two Monte Carlo simulation software. So as shown in figure 11,
On the left, I compare the simulation times for gate and MC square within 10 to the power of 7 and 10 to the power of 5 particles. And gate takes much longer, with over 10 hours for 10 to the power of 7 particles. And while MC square takes less than 30 minutes. And for 10 to the power of 5 particles, gate takes minutes and MC square only takes seconds. And on the right figure, the time differences is up to 70 times for 10 to the power of 7 particles and 30 times for 10 to the power of 5 particles. So overall, we can know that the MC square significantly reduce the computation time and improves the efficiency. And about my future work. So currently the research just focus on the homogeneous phantom, and with its future exploration, I will do the heterogeneous phantoms, and I will also address the activity distribution inconsistency between the MC square and gates in the proximal range. And about the MC square PE generates activity distribution, but the actual path results are influenced by scanner types. So I will also plan to develop the dual panel projection and reconstruction models to compare the predict and clinical path distribution. And that's all my presentation today. Thank you.
Does anyone have questions? Please.
MC square is an optimized Monte Carlo method that it can support the parallel computing across the multiple CPU. So it's designed to run efficiently on next generation Exxon processor to enhance its computation performance.
This experiment they use PET image, and in your opinion, do you think it's better to use PET MRI image to get the absolute boron concentration?
I don't know about is it better in a boron concentration, but why I use PET for dose verification is because it can produce the positron emission, but MRI cannot produce the positron emission. So I'm not sure it will be better or not. Because I'm focused on doing a dose verification for photon therapy. Figure 7. Figure 7 shows it is the lateral dose distribution from the low energy 70 MeV to 210 MeV, and it's compared with the Gates Monte Carlo simulation and the RayStation. RayStation is the clinical use software, so we want to compare about the Monte Carlo simulation and the clinical use, just like fit together to see the the lateral dose distribution is the same or not. But we can see here in 70 MeV they have the big range have different modes, but in high energy like 200 or 210 MeV they have a small difference. And the differences is because they have different calculation model between GATE and the MC square. But as we can see, the rate station and MC square is quite the same. So it means like MC square is for the clinical use software.
Because the photo-induced liquid lights are quite short half-life lights, so does the time impact your simulation or your future clinical ventilation?
Because it's like after the patient do the irradiation of proton therapy, the patient will do the offline PET. So when patients get the PET and it will like when the patient like scan the PET and it will activate the positron emitting nuclear inside the patient, so it's from the patient. And when we scan the PET, we can also detect these isotopes. So, because it's like prime gamma is also a second nuclide, and we cannot detect it because it's too fast. But about the positron emitting nuclide, we can detect it when we scan the PET.
Okay, I have a question. In page 13. Oh, I want to ask, what is the superimposed results mean?
It's just one.
You like pile up the image results.
It's just to want to say that we can simulation, we can simulate the positron distribution from the Cisco software, like in it.
Okay, thank you. Questions? Let's conclude our presentation.
我们这学期的那个 seminar 就到这边就结束哈。那我想，因为接下来同学应该就是要1年级同学应该就是要准备考试嘛，2年级的同学就是应该是准备要口试的一个部分哈。那大家应该了解，就是针对这2个不同的口试的内容要怎么准备嘛？哈，就是预口试的部分其实是你要说出一个架构，然后要说服口试委员说为什么你要做这些事情，然后你要告诉他们说做这些事情你预期可以克服现在的什么样子的一个困境，或者是技术上面的一些突破。那但是在口试的时候，就是 follow 你的预口试的这些实验的架构，告诉大家说你一步一步完成了什么事情。但最重要的部分就是还是讨论的部分，因为像这边是讨论人家的发表嘛，所以他怎么说，我们大家同学问的问题可能都是 paper 上面他们自己的自己去想出来的一些的一些讨论的过程。可是对于你们自己的 data， 你们自己就要有想法，就是说，实验为什么会失败？或者是说，为什么不如预期等等，这个就是很多的 discussion 的部分，你们可以再度去延伸所以其实预口试跟口试的这些准备方向就不是很不会很一样，那就是希望同学就是说在整个这个 seminar 的这些训练的过程里面，至少啦，你们在这个报告的内容里面，至少不会犯很多就是这种我们一直去提醒的小错误嘛，比如说字放的太多然后每一张图你要有个小小的 conclusion 对不对？然后整个的前言，然后 material 不一样或者 discussion 的这些架构应该都不会有问题。好，所以就是先预祝同学们就是预口试顺利，口试也顺利，然后就是该毕业的就要毕业了。好，那就下学期再见啦。好。 用。所以如果那个提问的次数有问题的话，再跟助教这边反映。他已经有公告次数嘛，对不对？好，所以大家应该都有掌握那个发问的次数哈。